For a long time, we believed we had a fairly solid picture of the universe. We knew its age. We knew its size. We believed we understood how galaxies formed, slowly, patiently, over billions of years. The universe, it seemed, followed a predictable story. Then James Webb started looking where no one expected to find much of anything. Not at the bright stars, not at the familiar galaxies, but into regions of space that appeared almost empty. Places we assumed were still young, quiet, unfinished. What Webb saw didn't look unfinished at all. Light was already there. Faint, stretched, ancient light, but far too much of it. Galaxies appeared where theory said they shouldn't exist yet. Not small, fragile beginnings, but structures that looked surprisingly mature. Bright, dense, active. At first, it was tempting to think this was just a better picture. Sharper images, more detail. But it wasn't that simple. James Webb didn't just show us more of the universe. It showed us something different. Data that didn't quite fit the timeline we trusted. Patterns that formed faster than we thought possible. A universe that seemed ahead of schedule. To understand why this changes everything, we need to start with something simple. How we see the universe at all. When you look up at the night sky, it feels immediate. The stars seem present, fixed, as if they are shining for you right now. But that feeling is an illusion. As you already know, light does not arrive instantly. It travels at a finite speed, about 300,000 kilometers per second. Fast by human standards, but slow enough that distance quietly turns into time. The moon you see tonight is already old. Its light left the surface about 1.3 seconds ago. The sun you feel warming your skin each day is not happening in real time either. That light began its journey 8 minutes earlier, long before it reached your eyes. Now extend that idea farther. When you look toward the center of our galaxy, the Milky Way, you are not seeing it as it is. You are seeing it as it was 26,000 years ago. At that moment, early humans were painting on cave walls. Civilizations had not yet formed. And yet, the light from the galaxy's core was already on its way toward us. This is the rule, not the exception. The farther you look into space, the farther back in time you are looking. The night sky is not a snapshot of the present universe. It is a layered archive, light stacked upon light, each ray carrying information from a different era. Every photon you see has a history. It remembers where it came from. It remembers when it was emitted. And it carries that memory across vast distances, unchanged, until something, your eye, a telescope, a detector, finally catches it. This is why astronomers often say that light is a messenger, not just a signal of brightness or color, but a record of time itself. When we study distant galaxies, we are not observing them as they exist today. We are watching earlier chapters of their story, sometimes billions of years before the present moment. This is also why the universe can never be seen as it is. There is no single cosmic now. Every direction you look points to a different moment in the past. The nearby universe feels recent. The distant universe feels ancient. And between them is a smooth, continuous gradient of time. Once you truly understand this, something subtle changes. The sky stops feeling static. It becomes dynamic, alive with history. And suddenly, the most important question is no longer what we see, but how far back we are seeing. Because if light is the only way the universe communicates its past to us, then everything we know depends on what kinds of light we can actually detect. Visible light shows only a narrow slice of that story. It captures stars like our sun and galaxies relatively close to home. But the oldest light, the light from the earliest galaxies, has been stretched by the expansion of space itself, pulled into longer wavelengths, shifted beyond what human eyes can perceive. Seeing the past only works if you can catch the right kind of light. And that is where the real story begins. But seeing the past only works if you can catch the right kind of light. Before we talk about what James Webb has seen, it's worth pausing for a moment. Because James Webb is not just another telescope. It is the result of 25 years of work carried out by thousands of scientists, engineers, and technicians across the world. It is a collaboration that spans continents, bringing together NASA, the European Space Agency, the Canadian Space Agency, and the Space Telescope Science Institute, along with research centers, universities, and aerospace companies worldwide. When James Webb finally launched, it carried more than instruments into space. It carried decades of design decisions, compromises, failures, redesigns, and patience. The project ultimately cost around $10 billion. James Webb is the largest and most powerful space telescope ever deployed. Its total mass is over 6.3 tons, and its sensitivity is roughly 100 times greater than Hubble's. That increase in sensitivity comes from one critical difference. James Webb does not rely on a single solid mirror. Instead, it uses 18 hexagonal mirror segments, each precisely shaped, aligned, and coated with a thin layer of gold. When combined, those mirrors form a reflective surface more than 6.5 meters in diameter, nearly 3 times wider than Hubble's mirror. That size matters, because the larger the mirror, the more light you can collect. And when you are trying to detect light that has traveled for billions of years, every photon counts. But mirror size alone is not what makes James Webb different. The real difference lies in what kind of light it was built to see. As you already know, light does not remain unchanged as it moves through the universe. Space itself is expanding, and as it expands, it stretches the light traveling through it. This stretching is known as redshift. It doesn't require equations to understand. Imagine drawing a wave on a rubber band. As you pull the band apart, the wave becomes longer and more spread out. The same thing happens to light. Light emitted by distant galaxies begins its journey at one wavelength. But as space expands, that wavelength is stretched into something longer, shifted toward the red end of the spectrum. For the most distant and ancient galaxies, the stretching becomes extreme. Light that was once visible is pulled into the infrared. This is where the story quietly breaks from what we were able to do before. Hubble was a remarkable telescope. It transformed astronomy for more than 3 decades, but Hubble was designed primarily to see visible and ultraviolet light. That made it perfect for studying stars, nebulae, and relatively nearby galaxies. But it also meant that the most ancient light, the light from the earliest structures in the universe, slowly slipped beyond its reach. By the time that light arrived near Earth, it had been stretched too far. Hubble wasn't missing those galaxies because they weren't there. It was missing them because it wasn't looking at the right wavelengths. James Webb was built specifically to solve that problem. It observes almost entirely in the infrared. And to do that effectively, it must operate at extremely low temperatures. Heat creates noise, and infrared telescopes are especially sensitive to that noise. So James Webb carries a massive, multi-layer sun shield about the size of a tennis court, designed to block heat from the sun, Earth, and Moon. On the cold side of that shield, Webb's instruments cool to just a few tens of degrees above absolute zero. In that cold, quiet environment, faint infrared light becomes detectable. This is why James Webb doesn't simply see farther than Hubble. It sees earlier. It catches light that has been traveling since the universe was young. Light that has been stretched, weakened, and transformed by billions of years of cosmic expansion. And because its mirror is larger, its detectors are more sensitive and its instruments are optimized for infrared wavelengths. Webb can collect enough of that light to form real images and real data. This is not about sharper pictures. It's about accessing an entirely different chapter of the universe's history. Hubble showed us how galaxies look once they are well established. James Webb is showing us galaxies while they are still assembling, while the universe itself is still finding its structure. And that difference matters, because when you finally observe the universe at the right wavelengths, with the right sensitivity, something unexpected happens. The timeline begins to look different. And the light arriving at Webb's mirrors tells a story that doesn't quite match what we thought we would see. That is why James Webb is not simply an upgrade. It is a shift in perspective. Long before the first stars ignited, the universe already existed in a very different state. It was not dark. It was too bright to see through. In the earliest moments after the Big Bang, everything was compressed into an extremely hot, dense environment. Temperatures were so high that stable atoms could not exist. The universe was filled with a glowing plasma, a restless mixture of free electrons and protons moving at tremendous speeds. In that state, light had no clear path. Each time a photon tried to move forward, it collided with charged particles. Scattered, redirected, trapped, light existed everywhere, yet it could not travel freely. The universe was opaque, more like the interior of a star than the empty space we imagine today. As the universe expanded, it slowly cooled. Over hundreds of thousands of years, conditions changed just enough for a crucial transition to occur. Electrons began to combine with protons. This moment is known as recombination. For the first time, stable atoms, mostly hydrogen and helium, could form. And once those atoms appeared, the constant scattering stopped. Light was finally released. Photons that had been trapped since the earliest moments of the universe were suddenly free to move in straight lines, beginning journeys that would last billions of years. That ancient light is still traveling today. We detect it as the cosmic microwave background, a faint, nearly uniform glow that fills the entire sky. It is not light from stars. It is not light from galaxies. It is light from a time before either existed. The cosmic microwave background gives astronomers a rare anchor point, a precise moment when the universe changed from an opaque fireball to transparent space. Before this moment, the universe could not be observed. After it, the universe became readable. But this first light did not make the universe bright. There were still no stars, no galaxies, no visible structure. What followed was a long, quiet era, filled with neutral gas and fading radiation. A period when gravity worked silently, shaping matter in ways that could not yet be seen. This early transition matters because it reveals something subtle. Light came first, structure came later, and between them was darkness, not as emptiness, but as a necessary stage. A stage the universe had to pass through before it could begin to shine in a meaningful way. And after that first light faded, the universe entered a long, quiet darkness, After the cosmic microwave background was released, the universe entered a phase we call the Dark Ages. By then, the first light from the beginning had already faded, stretched into the infrared and beyond. No stars were shining, no galaxies existed. The universe was an immense ocean of neutral hydrogen and helium, drifting in near total silence. But beneath that calm surface, something was working. Gravity. For hundreds of millions of years, gravity worked patiently. It searched for places where the gas was just slightly denser than its surroundings. It began pulling those regions together. Enormous clouds of gas started to collapse, growing denser and hotter under the crushing pressure of their own weight. Deep inside these clouds, a physical turning point arrived. Temperature and pressure rose so high that hydrogen atoms began colliding and fusing, releasing staggering amounts of energy. And then the darkness was torn open. The first stars ignited. This was the beginning of reionization. Ultraviolet light from these primordial stars pushed through the thick fog of gas, knocking electrons free from atoms and making the universe transparent again. According to the most advanced computer models we had, this process should have unfolded slowly. The first stars were expected to be huge, isolated, and short-lived. It should have taken a long time for them to gather into larger structures, into the galaxies we recognize today. That was the story we trusted for so long. A story of patience, a universe building itself step by step, from small to large, from simple to complex. But when James Webb aimed its mirror toward the edge of this dark age, it didn't find a half-finished construction site. It found something else entirely. If you're still here with us, thank you. We truly appreciate you taking this time to explore the universe together. We hope this video has given you something valuable. Not just information, but a clearer way of seeing how vast and fascinating the cosmos really is. We're always listening, always learning, and always trying to make these journeys deeper and more meaningful for you. If you'd like to support what we do, a simple like, a subscription, or sharing this video helps more than you might think. It allows us to keep creating thoughtful, carefully crafted stories about the universe. And without keeping you waiting any longer, let's continue our journey into what comes next. Before James Webb, astronomers shared a fairly consistent expectation about the early universe. After the cosmic dark ages, the first stars were supposed to appear slowly. Those stars would gather into small, faint galaxies, primitive systems still struggling to take shape. Time was the limiting factor. Gravity works patiently. Gas must cool. Matter must collapse and settle before anything complex can form. So when James Webb began observing galaxies at extremely high redshifts, looking back to when the universe was only 300 to 500 million years old, the expectation was clear. What appeared instead was unexpected. Webb did not find a sparse population of dim, fragile objects. It found galaxies that were already bright, already massive, already forming stars at a remarkable rate. These were not tentative beginnings. What made this more unsettling was that it wasn't just one object. Across different regions of the sky, Webb kept seeing the same thing. Galaxies with similar brightness, similar structure, and similar signs of rapid growth. A pattern was emerging. To understand why this mattered, astronomers compressed the universe's history into a simple comparison. Imagine the entire 13.8 billion year history of the universe, reduced to a single calendar year. In that scale, the first galaxies were expected to appear sometime in mid-January, slowly and unevenly. but the galaxies Webb detected were showing up around January 2nd, fully formed. That difference is not subtle. In cosmic terms, it represents an enormous shortage of time. Stars must ignite, gas must organize, structures must stabilize. Each of these steps is limited by physical processes that cannot be rushed. At first, astronomers questioned the result. Could dust be making these galaxies appear brighter than they were? Could gravitational lensing be exaggerating their size? Could distance estimates be off? Those possibilities were tested, and as additional observations arrived, the same conclusion kept returning. This was not a measurement error, and it was not an isolated case. The early universe appeared to be building complex structures far more efficiently than expected. This did not mean gravity had failed, or that known physics was broken, but it did suggest that the timeline we had relied on was incomplete. Something about the early universe allowed matter to organize itself faster than our models predicted. That realization marked the first serious crack in the old picture. These galaxies didn't just appear early, they appeared complete. And as astronomers looked closer, the picture only grew more difficult to explain. And the more closely astronomers looked, the stranger the picture became. The shock of James Webb wasn't only in what the galaxies looked like, it was in what they were made of. Images can mislead. Brightness can be boosted by dust. Distance can be complicated. But chemistry is harder to argue with. When Webb studied these early galaxies, it didn't just take pictures. It analyzed their light, splitting it into a spectrum like a fingerprint. And inside that fingerprint, astronomers began to see something unexpected, not just hydrogen, not just helium. They found signs of heavier elements, carbon, oxygen, nitrogen. That changes the story immediately, because the Big Bang did not produce those elements in any meaningful amount. The early universe was mostly hydrogen and helium, with only trace amounts of anything heavier. To get carbon, you need stars. Carbon is forged deep inside stellar cores, under pressures and temperatures no laboratory on Earth can reproduce. Oxygen is built the same way. Nitrogen as well. And those elements don't simply appear. They have to be made and then released. That means stars had to form, burn through their fuel and die, often violently, scattering these new elements back into space. Only then can the next generation of stars be born from enriched gas. So when Webb detects carbon and oxygen in galaxies this early, it implies something astonishing. Not one generation of stars, but multiple generations, in a universe that was only a few 100 million years old. It's like opening an oven you believe has never been turned on, and finding ash inside. Ash doesn't come from cold air. It comes from fire that has already happened. This is why the discovery felt so unsettling to astronomers. The galaxies weren't just bright too soon. They were already chemically mature, and chemistry carries a timeline. You don't get carbon without stars, and you don't get stars without time. Which left the community with a difficult question. If the universe was already chemically rich this early, what else about our formation story is incomplete? At this point, astronomers had to ask a difficult question. By this point, the question was no longer what James Webb was seeing. It was why our models hadn't predicted it. For decades, astronomers have relied on a standard picture of how galaxies form. In that picture, matter in the early universe starts out distributed almost evenly. Tiny differences in density, left over from the Big Bang, give gravity something to work with. Over time, gravity pulls matter together. Gas falls into dark matter halos. It cools slowly. Stars form gradually. Galaxies assemble piece by piece. The key word in all of this is slowly. That expectation is built into the models at every level. How fast gas can cool, how efficiently stars can form, how quickly dark matter halos can grow and merge. Each step is constrained by physics that doesn't change easily. And yet, the galaxies Webb was observing didn't seem to follow that pace. They appeared too massive, too bright, too developed, too early. At first, astronomers did what science always does when something doesn't fit. They questioned the data. Could gravitational lensing be magnifying these galaxies, making them look larger than they were? Could dust be affecting their colors and brightness? Could redshift measurements be off? Those possibilities were examined carefully. Different teams reanalyzed the observations. Alternative explanations were tested. Independent measurements were compared. The result was not a dramatic reversal. The uncertainties mattered, but not enough. Even when conservative assumptions were applied, the core problem remained. The galaxies were still there. Still bright, still early. That's when the focus began to shift. If the data were not fundamentally wrong, then perhaps the issue lay elsewhere. Not with gravity itself, not with the laws of physics, but with the assumptions we had made about how efficiently the early universe could turn matter into structure. Maybe gas cooled faster under primordial conditions. Maybe star formation was more intense in early dark matter halos. Maybe feedback processes behaved differently before the universe was chemically enriched. None of these ideas overthrow physics. They refine it. This is what a real scientific tension looks like. Not a crisis, not a collapse, but a mismatch between observation and expectation that demands closer inspection. And the most important realization was this: these galaxies were not isolated curiosities. They formed a pattern. Across different surveys, across different regions of the sky, across different observing strategies. This wasn't a single anomaly. It was a consistent signal that something in our timeline was off. The shock phase was over. What followed was investigation. And nowhere was this tension more visible than in the hearts of these early galaxies. The tension didn't stop at galaxies. At the centers of many of these early systems, James Webb revealed something even harder to explain. Black holes, not small ones, not early seeds just beginning to grow, but supermassive black holes, already weighing hundreds of millions of times the mass of the Sun, present when the universe was still extremely young. That immediately raised a problem. Black holes grow by feeding. Gas falls inward, heats up, and radiates energy before crossing the event horizon. But this process has a natural break. As radiation builds up, it pushes back against incoming material. That balance sets the Eddington limit, a maximum rate at which a black hole can grow under normal conditions. Even under ideal circumstances, that limit makes rapid growth difficult. Yet Webb was seeing black holes that appeared to have reached enormous masses far too early. And importantly, this wasn't a one-off discovery. These black holes kept appearing, embedded within the same early galaxies that already looked too mature. A pattern was forming. To explain it, astronomers explored several possibilities. One idea is direct collapse. Instead of forming from dying stars, some black holes may have formed when massive clouds of gas collapsed all at once, skipping the stellar stage entirely. That would create a much heavier black hole from the beginning. Another possibility involves massive seeds. The first stars may have been far larger than those we see today. When they died, they could have left behind unusually massive black holes, giving growth a head start. There is also the possibility that frequent mergers in the dense early universe helped accelerate growth, though this alone cannot fully account for the observed masses. Each idea helps. None fully solves the timing problem. What made this especially important was the context. These black holes weren't rare exceptions. They appeared alongside early galaxies that were already forming stars rapidly and showing chemical maturity. In other words, the galaxies weren't just assembling early. Their central engines were already active. These black holes didn't slowly grow into dominance. They appeared already massive. And supermassive black holes don't remain passive. They influence how galaxies evolve. They regulate star formation. They shape how gas flows through entire systems. So if black holes reach such sizes this early, the early universe must have been far more dynamic and far more efficient than expected. This wasn't a separate mystery layered on top of the galaxy problem. It was part of the same story. A universe building complexity faster than our timelines allowed. To understand what that really meant, astronomers had to step back and start counting the universe itself. By now, the discoveries from James Webb were raising an obvious question. How do astronomers actually know how many galaxies exist? After all, no telescope can scan the entire sky in perfect detail. The universe is simply too large. So instead of counting everything directly, astronomers rely on sampling. They focus on extremely small regions of the sky, areas that look almost empty at first glance, and study them in extraordinary depth. These observations are called deep fields. A deep field is created by pointing a telescope at a tiny patch of sky and letting it collect light for days or even weeks. Photons that would normally be too faint to detect slowly accumulate. What begins as darkness fills with structure. Dots appear. Smudges take shape. Each one is a distant galaxy. Once astronomers count how many galaxies appear in that small patch, they use a simple idea. If the universe is roughly uniform on large scales, then that tiny region should be representative of many others like it. Count the galaxies in the sample. Measure the area of the sky it covers. Then scale up. This method has worked remarkably well. It's how astronomers arrived at the familiar estimate of hundreds of billions of galaxies in the observable universe. And for a long time, there was little reason to doubt it. The universe, when viewed broadly, looks statistically smooth. No region appears dramatically special. No direction dominates. But this method has an important limitation. It can only count what the telescope can see. Earlier surveys relied heavily on visible and ultraviolet light. They were excellent at detecting bright, nearby galaxies, but far less sensitive to faint, distant ones. That meant the sample itself was filtered, not intentionally, but inevitably. The farther back in time astronomers looked, the more galaxies slipped below the detection threshold. So while the method was sound, the data feeding into it may not have been complete, which raises a quiet but unsettling possibility. What if the universe was never sparse at early times? What if our samples simply missed much of what was there? We never counted the universe directly. We estimated it. And when James Webb looked at the same patches of sky, using different light, greater sensitivity, and far deeper reach, the picture changed dramatically. And when James Webb looked at the same patches of sky, the picture changed dramatically. When James Webb turned its attention to the same deep fields astronomers thought they already knew, the change was immediate and unmistakable. These were not new targets. They were familiar regions of sky, studied for years by earlier telescopes. With Hubble, many of these fields appeared quiet, dark, sparse. Not because nothing was there, but because most of the light had slipped beyond what Hubble could see. As the universe expands, ancient light stretches. Wavelengths lengthen. Visible light fades into the infrared. By the time that light reaches us, it no longer looks bright and blue. It arrives dim, red, and subtle, easily missed by instruments designed for shorter wavelengths. James Webb was built for exactly this kind of light. So when it looked again, the darkness changed character. Where Hubble saw emptiness, Webb saw structure. Faint points emerged across the frame, then more, then far more than expected. Galaxies began to fill the image, not bright spirals or familiar shapes, but small, reddish smudges, each one ancient, each one distant, each one a record of an early universe. In a single Webb deep field, astronomers counted hundreds of thousands of galaxies, all within a patch of sky so small it's hard to describe. Hold a grain of sand at arm's length. That's larger than the region Webb was studying. And yet, within that tiny area, the universe appeared crowded. The implication was hard to avoid. The early universe was not sparsely populated by a few isolated systems. It was dense with galaxies, many of them too faint, too red, and too distant to have been detected before. This wasn't about improved sharpness. It wasn't just a clearer picture. It was a different census. Webb's images were so rich in detail that seeing everything at once became impossible. To study them properly, astronomers had to zoom in. Then zoom again. Individual frames, when printed at full resolution, would need to be displayed at the size of a wall to capture every galaxy. The darkness hadn't been empty. It had been invisible. And that distinction matters. Because all the earlier estimates of how many galaxies existed, especially in the early universe, were based on what telescopes could detect at the time. When the detection threshold changed, the numbers changed with it. Not slightly, dramatically. Suddenly, the idea that the early universe was slow and underpopulated became difficult to defend. There were simply too many galaxies, too early, too close together. This wasn't a minor correction or rounding error. It was a fundamental shift in how crowded the universe appeared when it was young. Once astronomers realized how much had been hidden in plain sight, the implications began to stack up. If there were far more galaxies than expected, if stars were forming rapidly across countless systems, and if black holes were already active at their centers, then the early universe was not quietly assembling itself. It was busy, and understanding just how busy it was would force astronomers to rethink more than just the numbers. Once astronomers realized how crowded the universe really is, the implications became impossible to ignore. As the picture grew more crowded, another realization followed naturally. The universe is not arranged at random. Galaxies do not scatter evenly through space like grains of dust. They follow patterns, large, repeating structures shaped by gravity over billions of years. This vast arrangement is known as the cosmic web. On the largest scales we can measure, matter organizes itself into long filaments, thread-like structures stretching millions of light years across space. Along these filaments, galaxies line up like beads. Where multiple filaments intersect, matter piles up. These intersections become nodes, dense regions where clusters of galaxies form. And between the filaments lie enormous voids, regions with very few galaxies at all. The result is a universe that looks less like a cloud and more like a woven fabric. This structure didn't appear by chance. It emerged because gravity amplified tiny differences in density left over from the early universe. Where matter was slightly denser, gravity pulled harder. Over time, those regions grew into filaments and nodes, while surrounding areas emptied out. For decades, astronomers could only infer this structure indirectly, through simulations and large galaxy surveys. James Webb began to change that. By observing faint, dust-obscured galaxies and extremely distant systems, Webb helped reveal early versions of this cosmic architecture. It detected protoclusters, regions where galaxies were already gathering when the universe was still young. Not fully formed clusters, but unmistakable beginnings. These early structures showed that the Webb was assembling faster and earlier than expected. Galaxies weren't forming in isolation. They were forming within a framework, guided by invisible pathways of mass. This helps explain much of what Webb has revealed so far. If galaxies are born inside dense filaments, then gas doesn't drift aimlessly through empty space. It flows. It concentrates. It feeds star formation efficiently. In such an environment, rapid growth becomes more likely. The cosmic web brings order to what initially looked like chaos. It shows that the early universe wasn't a scattered collection of objects appearing at random times. It was a structured system, developing according to deep gravitational rules. The universe isn't scattered, it's woven. And that realization leads to an even deeper question. Because the filaments themselves, this vast skeleton shaping everything we see, are not made of ordinary matter. They point to something else entirely. Something that doesn't emit light, doesn't absorb it, and yet controls the architecture of the cosmos. And this hidden structure points to something we cannot see at all. If the universe is woven into a cosmic web, then the obvious question is simple. What is the thread made of? Because ordinary matter, stars, gas, dust, doesn't have enough mass to build a structure this large, this stable, and this organized on its own. The cosmic web needs a scaffold, something that can collapse early, pull matter inward, and hold shape over time. That is where dark matter enters the story. Dark matter does not shine. It does not absorb light. It does not reflect it. You can point the most powerful telescope at it and see nothing. And yet, it reveals itself through one unmistakable effect: gravity. Dark matter interacts primarily through gravity. It adds mass without adding light. We don't detect it directly. We infer it from what it does to things we can see. One line of evidence comes from galaxy rotation curves. In many galaxies, stars far from the center move faster than they should, if only visible matter were present. By the standard rules of gravity, those outer stars should slow down. They don't. It's as if an invisible halo of mass surrounds the galaxy, providing extra gravitational pull. Another clue comes from gravitational lensing. Mass bends space. And when a massive object sits between us and a distant galaxy, it can warp and magnify that background light. Sometimes the distortion is subtle. Sometimes it forms arcs and stretched shapes. When astronomers map that lensing, they often find that the mass responsible is far greater than what visible stars and gas can explain. A third clue comes from galaxy clusters, the largest bound structures in the universe. Clusters behave as if they are held together by far more mass than we can see. Without that extra mass, they would not remain stable. Taken together, these clues point to the same conclusion. Most of the universe's structure is built from something invisible, and in the early universe, that invisible matter matters even more. dark matter began to clump first. While ordinary gas was still hot and resistant to collapse, dark matter could start forming gravitational wells, invisible halos that acted like containers. Over time, normal matter fell into those halos. Gas pooled, it cooled, it became dense enough for stars to ignite. So galaxies did not form randomly in open space. They formed where dark matter had already prepared the ground. This is why the cosmic web makes sense. The filaments are not made of glowing material. They are highways of mass, mostly dark matter, guiding where galaxies can form and how they can grow. And this is where James Webb fits back into the picture. Webb cannot see dark matter directly, but it can see the galaxies tracing its outline, lining up along filaments, gathering at nodes, assembling earlier than expected. What we see is built on something invisible once you accept that. The early universe begins to look less mysterious, not calm, not slow, but structured, shaped by a hidden framework from the very beginning. But structure alone doesn't explain how big the universe really is. But structure alone doesn't explain how big the universe really is. Here is one of the most common misunderstandings in astronomy, especially when people first hear the age of the universe. The universe is about 13.8 billion years old. So a reasonable instinct is to say, if light has been traveling since the beginning, then the farthest we could possibly see should be about 13.8 billion light years away. That sounds logical. It's also wrong, because it assumes the universe is a fixed stage, unchanging while light travels across it. But space is not static. Space expands, and it has been expanding for the entire journey that light has been taking. So when the first light in the universe began traveling outward, it wasn't crossing a calm, unmoving distance. The distance itself was stretching underneath it. A useful way to picture this is with a balloon. Imagine tiny dots drawn on the surface of a balloon. As you inflate it, the dots move farther apart. Not because the dots are crawling across the rubber, but because the rubber between them is expanding. Or imagine a line drawn on a strip of elastic. If you pull the elastic while a tiny bead is sliding along the line, the bead is moving forward. But the line is also getting longer as it goes. That is what light has been doing in our universe. Light travels at a constant speed through space. But the space it travels through has been growing. So the photons reaching us from the early universe started their journey when the source was much closer. And during the time those photons were in transit, the universe expanded. The result is a distance that is larger than the simple age-time speed calculation. Today, the radius of the observable universe is not 13.8 billion light years. It is about 46.5 billion light years, which means the observable universe is about 93 billion light years across. That number can feel impossible at first. It sounds like something must be breaking the speed limit, but nothing is. No galaxy is racing through space faster than light in the way a spaceship might. The key is that this is not about objects moving through space. It is about space itself expanding. In general relativity, that distinction matters. There is no rule that says the distance between far separated regions of space cannot grow. The speed limit applies to motion through local space, not to the expansion of the space between distant points. And this is why the universe can be far larger than its age seems to allow. The age tells you how long light has had to travel, but the size you can observe depends on what happened to space during that travel. Distance in the universe is not just about how far, but how long, and how space changed along the way. Once you grasp this, another idea becomes unavoidable. If the universe is expanding, and if there is a maximum distance from which light has had time to reach us, then there is a boundary to what we can ever observe. Not because our telescopes are weak, but because the universe itself sets a limit. And that expansion creates a boundary we can never cross. And that expansion creates a boundary we can never cross. Once you understand how the universe can be larger than its age suggests, another idea follows naturally. There is a limit to what we can ever observe. This limit is called the cosmic horizon. It is not a wall. It is not an edge in space where things stop existing. It is a boundary of causality, a line drawn not by distance alone, but by time and expansion. The cosmic horizon marks the farthest regions from which light has had enough time to reach us and still reach us at all. Beyond that horizon, galaxies still exist. Stars are still forming. Planets may still be assembling. But their light will never arrive here. Not because it was never emitted, and not because it is blocked, but because the space between us and those regions is expanding too quickly. As the universe grows older, its expansion has not slowed down. It has accelerated. That acceleration stretches space so rapidly that light emitted beyond a certain distance is carried away faster than it can close the gap. The photons are always moving forward at the speed of light, but the space they are traveling through is pulling them farther behind. So there are regions of the universe whose light is already on its way toward us, and regions whose light will never arrive, no matter how long we wait. This is the cosmic horizon. It is important to understand what this does not mean. It does not mean there is an edge to the universe itself. It does not mean the universe ends where our vision fades. It means our access to the universe is limited. No telescope can change that. James Webb cannot see past the cosmic horizon. Neither could any future instrument, no matter how powerful. This is not a technological barrier. It is a physical one. The observable universe is only a portion of the whole. The region that happens to be in causal contact with us. Everything beyond it is real, but unreachable. This idea can feel unsettling at first. We like to think that better tools will eventually reveal everything, that patience and progress can overcome any limitation. But the cosmic horizon reminds us that some boundaries are built into the universe itself. And that doesn't diminish what we can know. It gives it context. Within this horizon lies every galaxy we will ever observe, every ancient photon we will ever detect, every structure James Webb has revealed, and every structure it ever will. Understanding this limit does not shrink the universe. It reframes it. It tells us that our cosmic moment, here, now, within this observable bubble, is special not because it is central or unique, but because it is accessible. The universe doesn't end at the horizon. Our access to it does. And that boundary, the one defining what can influence us and what cannot, is shaped by a force even more mysterious than dark matter, a force that governs the expansion of space itself. And that boundary is shaped by a force even more mysterious. If dark matter is the invisible scaffold that helps structure form, then dark energy is something else entirely. It doesn't build, it stretches. In the late 1990s, astronomers made a discovery that changed cosmology in a quiet but profound way. They were studying type Ia supernovae, exploding stars that can act like cosmic distance markers. Not because they are identical in every detail, but because their brightness follows a predictable pattern once calibrated. By comparing how bright these supernovae appeared to how red-shifted their light was, researchers could estimate how the expansion of the universe had changed over time. The expectation was reasonable. Gravity should slow expansion down. Matter pulls inward. Over billions of years, that pull should act like a brake. But the data said something different. The expansion wasn't slowing, it was accelerating. The universe was not coasting, it was speeding up. To describe whatever was driving that acceleration, cosmologists used a name that is still more label than explanation: dark energy. We do not see dark energy directly. We don't detect it in images the way we detect galaxies. We infer it from its effect on the expansion of space itself. And by the best current accounting, dark energy makes up roughly 68% of the universe's total energy content. That number can be surprising. We tend to think the universe is mostly made of the things we can point to: stars, planets, gas, dust. But ordinary matter is only a small fraction. Dark matter adds more. And dark energy dominates the long-term behavior of the universe. It's important not to confuse dark energy with dark matter. Dark matter behaves like extra mass. It pulls, it clumps. It helps gravity gather gas into halos and filaments. Dark energy does the opposite. It does not clump into structures. It doesn't form halos or filaments. Its role is more subtle and more global. It acts like a pressure built into space itself, pushing the universe to expand faster as time goes on. The simplest way to feel what that means is to think about distance over time. In an accelerating universe, the separation between faraway galaxies doesn't just increase, it increases at an increasing rate. And over very long timescales, this has a direct consequence for the cosmic horizon we just described. As expansion accelerates, more and more galaxies drift beyond the horizon, beyond the region from which light can ever reach us. Those galaxies don't vanish. They remain out there, continuing their own histories. But from our point of view, they gradually become unreachable. Their light grows fainter, more stretched, more red-shifted. Eventually, they fade beyond detection. Not because our telescopes fail, but because the universe's geometry carries their signals away. This can sound dramatic, but it's not a sudden event. It doesn't change the night sky in a human lifetime. It doesn't affect life on Earth. It is a slow unfolding over billions and trillions of years. The universe is not tearing itself apart tomorrow. What dark energy changes is our understanding of the long arc. It suggests that the distant future of the universe may be one where structures become increasingly isolated, where each galaxy group becomes an island in a growing ocean of space. And it adds a layer of meaning to our present moment. We live at a time when the universe is old enough to have formed complex structure, galaxies, stars, planets, but not so old that everything has disappeared beyond our horizon. We can still see deep into the past. We can still collect ancient light. We can still map the cosmic web. That window will not stay open forever. And that is not a cause for fear. It is a reminder that the universe has chapters. And we happen to live in one where the story is still visible. The future of the universe is shaped by something we barely understand. A force that dominates the expansion of everything, while remaining invisible to every instrument we build. And yet, it's not a reason to give up on understanding. It's a reason to be careful about what we think we already know. Because this is exactly the pattern James Webb has been revealing again and again. When we look with new eyes, the universe doesn't just become clearer. It becomes more complicated. in the most productive way. All of this brings us back to what James Webb truly changed. All of this brings us back to what James Webb truly changed. As dark energy continues to stretch space, its effects become most visible only on the longest timescales. Not years, not centuries, but billions of years into the future. Over that vast span of time, the universe will keep expanding faster and faster. And as it does, distant galaxies will slowly drift beyond the cosmic horizon. One by one, they will become unreachable. Not because they disappear, not because they stop forming stars, but because the space between us and them grows too quickly for their light to ever arrive. In the far future, observers living in our region of the universe may see a very different sky. Most galaxies outside the local group will have crossed beyond the horizon. The night sky will appear emptier, quieter. An astronomer born trillions of years from now might look up and see only a handful of nearby galaxies, perhaps just the merged remnants of the Milky Way and Andromeda. They would still see stars. They would still see planets. But the grand cosmic web would no longer be obvious. Even the evidence for the Big Bang itself would be difficult to recover. The cosmic microwave background would be stretched so thin, so faint, that it would fade into the background noise of space. This is not a disaster. It's not an ending. It's simply the long-term consequence of an accelerating universe. Nothing violent happens. Nothing collapses suddenly. The universe doesn't become hostile. It becomes quieter. What makes this realization meaningful is not the future itself, but the contrast with now. We live at a time when the universe is still readable. We can still see far beyond our local neighborhood. We can still detect ancient light released billions of years ago. We can still trace the filaments of the cosmic web and measure the expansion of space. This window is not permanent. It exists because of timing. The universe is old enough to have formed rich structure, galaxies, stars, heavy elements, but not so old that those structures have slipped out of view. That makes our moment unusual, not special in a cosmic sense, but fortunate. And this is where James Webb fits into the story in a deeper way. Webb was launched at a time when the universe is still willing to reveal its early chapters, when light from the first galaxies is still arriving, when the structure of the cosmos can still be mapped in detail. Future observers may have far more advanced technology, but they may have far less to see. We live in a brief era when the universe's history is still written across the sky, and Webb arrived just in time to read it more clearly than ever before. This isn't a reason for anxiety. It's a reason for quiet appreciation. The universe is not rushing toward silence, but it is slowly becoming more private. And that brings us back to what James Webb has truly changed. It didn't just show us new objects. It showed us when we are and why that matters. We live at a time when the universe is still willing to tell its story. By the end of this story, it's important to be clear about what James Webb did not do. It did not rewrite the laws of physics. It did not overturn gravity. It did not suddenly explain dark matter, dark energy, or the ultimate fate of the universe. Most of the foundations still stand. What Webb changed was something quieter and more profound. It changed the limits of what we can observe, and in doing so, it changed how we ask questions about the universe. Before Webb, our picture of cosmic history was shaped by what earlier telescopes could see. That picture was not wrong. It was incomplete. We believed the universe formed structure slowly. that galaxies took time to assemble, that stars lived long lives before enriching their surroundings, that black holes grew patiently, constrained by time and physics. Webb did not erase that story. It complicated it by extending our vision deeper into infrared light. Webb revealed a universe that was already busy much earlier than expected. Galaxies appeared sooner. They were brighter. They were more massive. Their chemistry showed that stars had already lived and died. Their centers contained black holes that had somehow grown large in a short span of time. And when we counted carefully, the universe turned out to be far more crowded than we had assumed. None of these discoveries stood alone. Together, they pointed toward a universe that builds structure more efficiently under early conditions than our simplified models allowed. That realization forced revisions, not dramatic overhauls, but careful adjustments. Timelines were stretched, densities were reevaluated. The roles of invisible components, dark matter and dark energy, became more central, not less. Webb showed us that the early universe was not a quiet prelude. It was an active phase, shaped by hidden frameworks and rapid processes we are only beginning to understand. But perhaps the most important change wasn't about galaxies, black holes, or cosmic distances. It was about method. James Webb reminded us that understanding the universe is not just about collecting answers. It's about asking better questions. Questions shaped by data rather than assumptions. Questions willing to let go of comfortable timelines. Questions that accept complexity instead of forcing simplicity. This is how science moves forward. Not by sudden revolutions, but by steady corrections guided by sharper observation. In that sense, Webb didn't deliver a final verdict on the universe. It opened a new chapter, one where the observable universe appears larger than we thought, older in some ways, more active in others, and one where our place within it feels both smaller and more meaningful. We are small, tiny observers on a single planet, orbiting an ordinary star. But we are also precise, patient enough to wait for faint photons that have traveled for billions of years, careful enough to measure tiny distortions in light, curious enough to question pictures that once seemed complete. There is no grand declaration at the end of this story. No final answer, only a quiet understanding. James Webb didn't change the universe. It changed how we understand it. And that change didn't come with drama or spectacle. It came through calibration, through spectra, through deep fields and careful counting. Through the realization that the universe is larger, earlier, and more complex than our previous snapshot suggested. And Webb is not finished. New observations are still arriving. New data is still being analyzed. And new questions are already forming. The story of the universe is still unfolding. We simply happen to live at a moment when it can still be read. And for now, that understanding is enough. And for now, that understanding is enough. Thank you for staying with us until this moment. If you're listening at the end of a long day, allow yourself to let go of whatever has been weighing on your mind. Settle into a comfortable place. Breathe slowly. Let your thoughts drift as the universe continues its quiet motion. There's nothing you need to do right now, nothing you need to solve. If you'd like, feel free to share your thoughts with us in the comments. We always enjoy hearing from you. Until next time, rest well and sleep peacefully.